Hey there folks, this is Ref Bari, Brown University Physics grad student. Welcome to the next episode of Physics GRE Lectures. Today I'm going to be solving a thermodynamics problem on an ideal gas undergoing isothermal expansion. So let's check out the problem. So the problem says we have an ideal gas that is undergoing the following expansion on a pressure volume diagram, PV diagram, and the ideal gas starts at some volume, let's call it VA, and it goes in isothermal, that means equal temperature at all points, an isothermal expansion to VB. And its original pressure is, let's say, PA. Its final pressure is, let's say, PB. And we're told that the ideal gas satisfies the following equation of state that links its initial pressure, PA, VA, to its final pressure, PB, VB, by the following power law. PV to the 5/3 is PB to the 5/3. Now, if this looks foreign to you, it should not, because recall, there are two main formulas for the ideal gas equation of state. First is the ideal gas law, PV is equal to nKT, which we can modify by using van der Waals equation, P minus AN squared times V minus NB is equal to nKT. Or alternatively, the second equation you should recall is that PV gamma is P prime V prime gamma, where gamma is the heat capacity constant given by Cp over Cv. What is Cp? What is Cv? Cp is the heat capacity at constant pressure. It's partial Q, partial T at constant pressure. Likewise, Cv is partial Q, partial T at constant volume, the heat capacity at constant volume. So, heat capacity at constant pressure simply measures how much your system's temperature changes if you add a little bit of heat. In other words, how heat sensitive is your system? How sensitive is your system to a little bit of heat at constant pressure? That's the exact same idea for Cv, but at constant volume. We can, of course, use the first law of thermodynamics, which is simply the conservation of energy, which says that energy for a thermodynamic system can only change in one of two ways. You can either add heat or you can do work. We can use this to simplify our equation for Cv further, because if we're at constant volume, there is no work done on the system. This is zero. That means du at constant volume is equal to dq, which means that Cv is simply du dt, simply the derivative of the system's internal energy. So if you can determine the internal energy of a thermodynamic system using the equipartition theorem, then you can just differentiate it with respect to temperature and obtain the heat capacity at constant volume. So now what we can do is take this over here and apply it to our situation here. We know that for an ideal gas, there are three different situations for the heat capacity. Here's what we know. If I draw the energy versus temperature of an ideal gas, I know that at very low temperatures, the energy of the ideal gas is simply 3/2 kT. It's simply the translational kinetic energy of the ideal gas. But if I heat the system up a little bit, then at about 1 degree Kelvin, the system will obtain a new type of energy, vibrational kinetic energy. And that comes out to about 5/2 kT. And if I now keep increasing the temperature, the system undergoes another change, and at about 100 degrees Kelvin, if I remember correctly, the system now has rotational kinetic energy, and that brings its total energy to about 7/2 kT, as we found out in a previous lecture. So that means the change in the energy of the ideal gas can actually change the heat capacity constant of the ideal gas. Think about what that means. Another equation, by the way, that you should know for an ideal gas, linking Cp to Cv is as follows. Cv minus Cp is equal to Nk. All right, so now let's take a look, apply this to the first situation here, 3/2 kT. At 3/2 kT, our question is, what is the heat capacity constant? In other words, what is gamma at very low temperatures? At very low temperatures, we have to determine Cp and Cv, but we already know at low temperatures, the energy is just 3/2 kT. So the heat capacity at constant volume is simply going to be partial U, partial T, constant volume. But we know that U is 3/2 nKT, so this is going to give us let me use black. This is going to give us 3 halves Nk. Okay? Now similarly, we can determine Cp by using this formula. By the way, I think I switched these up. This should be Cp, this should be Cv. So now, from the fact that Cp minus Cv is Nk, and I know Cv is 3 halves Nk, that means Cp is simply 5 halves Nk. And now I can determine the heat capacity constant, gamma, which is Cp over Cv. Now that's simply going to be 5 halves divided by 3 halves, or 5/3. So this is one possibility for the heat capacity constant. This is the possibility given in the initial statement of the problem. But we can also have a different situation. If we are at 1 degree Kelvin, so at very low temperatures, near 0 degrees Kelvin, we have just determined that gamma is 5/3. But at a slightly higher temperature, around 1 degree Kelvin, what is gamma going to be? Well, we know that the energy of the ideal gas is 5 halves kT. So again, using Cp minus Cv is Nk, using this relationship, and knowing that Cv is now going to be 5 halves Nk, now I know that Cp at about 1 degree Kelvin is going to be 7 halves Nk, meaning that gamma at about 1 degree Kelvin is going to be 7 halves Nk divided by 5 halves Nk, which is 7 over 5. So gamma at about 1 degree Kelvin is going to be 7 over 5. And finally, at the highest temperature, at about 100 degrees Kelvin, the energy of the ideal gas is 7 halves kT. Okay, so that means if I simply use this formula again, Cv minus 7 halves Nk is Nk, gives me that Cp at about 100 degrees Kelvin is 9 halves Nk, which, plugging into my gamma heat capacity constant formula, gives me 9 halves Nk divided by 7 halves Nk is equal to 9/7. So that means the heat capacity of this ideal gas at about 100 degrees Kelvin is 9/7 Nk. Or actually, this is just a constant, so it's just 9/7. So the idea is the heat capacity can change from 5/3 to 7/5 to 9/7. It can be any three of these quantities. Thank you for watching this lecture, and we'll see you in the